So without further ado, I will introduce the first speaker, Keith Stockdale, who's going to be telling us about automated testing of shader code. Welcome, Keith.
Hello, nice to be here.
Hello. All right, take it away.
All right then. Okay, so this is automated testing of shader code at Rare. My name is Keith Stockdale, and I'm a senior software engineer at Rare. And I've given a talk on this topic just at this year's GDC, but this is going to have a bit more of a C++ spin on it. So a little bit about me first. This is me, in case my video quality is a bit poor. And if you're wondering, the accent's from Northern Ireland. That's where I'm originally from. And I've been working at Rare for the last 6.5 years on the engine and rendering teams. Basically, my whole job is just writing things on the GPU that probably shouldn't be run on the GPU. And at my time at Rare, I have worked on Sea of Thieves. Sea of Thieves is a game that we launched initially in 2018. It is our first Unreal Engine game, and it is based on a very heavily modified Unreal Engine 4.10, so quite old. And I said we initially launched in 2018 because we have been consistently putting out updates throughout the years. Just last week, we released a major update, and today, in fact, we released for the first time on PS5, which we're all very happy about. So still lots going on with Sea of Thieves, still very much in development. And alongside the development of Sea of Thieves, we also have Everwild. And Everwild is our up-and-coming game at Rare. And it's a little bit different with Sea of Thieves in that we are trying to stay up to date with the latest and greatest Unreal Engine. So currently, we're on Unreal Engine 5.2, and we're in the process of upgrading to 5.3. Okay, with all that out of the way, the problem. And the problem that we have at Rare is that we are writing more GPU code. And this GPU code is not your typical GPU code that outputs pixels. It's more general purpose simulation code. So just in Sea of Thieves, we have two very prominent GPU simulations. So the first is our FFT water simulation. So you can't really have a game called Sea of Thieves without having a very good looking sea. So that is all being simulated on the GPU. And then we also have our GPU particle simulation. So anything to do with fire or sparks, fireworks, smoke, bubbles, water spray, all of that type of stuff, that's all being simulated on the GPU. And with all of this general purpose code being executed on the GPU, we like to test it. And the reason for that is because we as a studio love automated testing. And we love it so much that we have given a number of talks on it, this one included. One particular talk was automated testing of gameplay features in Sea of Thieves by Rob Masella way back in 2019 at GDC. These are some links if you want to go to it. If a QR code's easier, there's a QR code, otherwise some words. But this is the main slides that I felt was the most prominent thing on his presentation, where he's talking about all the benefits that we have reaped from automated testing. So we've got things like reduced time to verify builds, so we get our content out to players much quicker. Lower bug count with comparison to previous Rare titles, and observably reduced crunch as well. So these are all the reasons why we like to do it. But Rob here was talking about testing of gameplay features, but I'm here to talk about testing of shader code. And if you don't know how to get started with testing shader code, this is a fantastic article by Bart Wronski. It's called How Not to Test Graphics Algorithms. And in it, he lays out two main ways of testing graphics algorithms. The first is screenshot testing, which is what we've been doing at Rare since before I started back in 2015. And then the second approach is what I'm going to be talking about today, which is shader unit testing. So our unit testing framework for shaders, we just called it Rare Shader Test, and it is a testing framework for HLSL codes. And if you don't know what HLSL is, it stands for High Level Shading Language, and it is the shading language that all DirectX applications uses their shading language. So if it's a DirectX app on the PC, or if it's an Xbox game, chances are the shader code will be written in HLSL. Our unit tests are written in HLSL 2015, so quite an old version. And the main reason for that is because our testing framework is being used for both Sea of Thieves and Everwild. So 2015 has a common feature set there, so we stick to that. And it runs on top of an Unreal testing framework. So this is not a standalone testing framework by all means. It is just adding on top of what Unreal already gives us, so that we can use all the nice tooling that Unreal provides, as well as letting us test our shader code. An example of the testing framework that we are building upon is CQ test, which stands for Code Quality Test. And because I know in the audience there are probably at most one or two people who actually know what this is, it's an Unreal Engine testing framework, like I said, and it's available from Unreal Engine 5.3 and on, so it's fairly recent. It's quite comparable to Microsoft's unit testing framework. And if you haven't seen it before, this is what a testing suite might look like with CQ test. So you have your test class macro at the top, and that defines the actual name of the test suite. And then you have any number of test methods within it, which are your actual tests that run. Within your test method, you'll have various assertions, basically just making sure all of your code works as you expect it to. And then in addition to test methods, you also have setup methods called before each. So these methods will be called before each test method, as well as after each. So that'll be called after each test method to do some cleanup. Now, before I go any further, I want to just make it clear what our coding environment is. Unreal Engine 5.2 currently, so we are upgrading soon, but very much still on 5.2. And that means we're in C++ 17 land. So we unfortunately don't get the nice C++ 20 just yet. That will be coming with 5.3. So another reason why I'm very excited about 5.3. And we are using HLSL 2015, as I said. Now, throughout the course of this talk, I'll be showing C++ code as well as HLSL code. So if you see the C++ symbol at the top right, it'll be C++ code on the screen. And if you see the HLSL doggo, you will be seeing HLSL code. Okay, then, on with actually showing how to write a shader unit test in our testing framework. So HLSL doggo at the top right, this is HLSL. So it starts off with some includes. So at the minute, it kind of looks like C++ with the includes. The first include is the header that all Unreal shaders must include. So there's nothing interesting there. Then we have the actual testing framework. I'll be talking a little bit more about that header later on. And then we have our system under test header, which is, in this case, the water particle framework. And then we have the first clue that this is not, in fact, C++. This is a shader. So this is an attribute that you tag on to the entry function of a compute shader to tell it how many threads to run per thread group. So this is a very simple shader. It is running a single thread. So not very good use of your GPU, but we don't really need it to be very fast. We just need it to be correct. And then we have the entry function. And we name the entry function the same name as the test. This just makes it easier to connect up the HLSL side to the C++ side. And at Rare, we like to use the given, when, then naming scheme for writing tests. So in this case, we have got giving moving water exists. So we construct some water with a known velocity. When the particle is spawned on the surface, so in this case, we're passing in water into this spawn function, and it returns us a water particle, then the velocity is inherited, so we assert that the spawn particle's velocity is in fact the velocity that we expect it to be. And that's basically it. So you've got your standard given, when, then that you might see in any other testing framework with any other language. Now, this is a shader, so we need some C++ code to dispatch the code itself. And we try to make sure this is as minimal boilerplate as possible. So we start off with the header of the testing suite, which looks like CQ test class macro, except it has an extra argument. And that argument is the path to the actual shader tests themselves. And then we have any number of test methods. So again, it's just giving the method and giving the name of it. So you can search that name and you'll find the C++ code as well as the HLSL code in your code base. Now, the shader I just showed is extremely simple. It has no external parameters to bind or anything like that there. It'll just run with nothing to provide in the C++ side. So all we need to do is call run compute shader test with the dispatch configuration. So if you're familiar with DirectX at all, this will be equivalent to calling dispatch 111. right? So it's dispatching a single thread group on your GPU. So it's a single thread group, and that single thread group will be running a single thread. So not very fast, not making use of your GPU in any way, shape, or form, but that's fine because the main thing we're concerned about here is testing our code on the actual hardware that it would be running on during your game. Now, at this point, I want to talk about the goals of the framework. And initially, I was going to talk about all of them, but just for the sake of time, I'm only going to talk about two. The first is we want our tests to be fully automatable. So I mentioned that we have screenshot testing for Sea of Thieves, and we've had that for ages. But the problem with it is it's not fully automatable. We do require our test team to verify screenshots from time to time to make sure everything is still right. However, that's not ideal. We'd rather them just get a green tick for happiness and red tick for sadness. So to demonstrate that this is actually something we can do now, we have this feature in Sea of Thieves, which is our calm water system. And what it'll do is, as you get closer to an island, it will smooth out the FFT water simulation. So in the distance there, you can see it's all very choppy. But then as you get closer, it smooths out quite considerably. And we have a full test suite just for this feature. And the nice thing about building on top of our testing framework in Unreal is that we get all the nice Unreal test running capabilities as well and reporting. So we can just open this up in our session front end like anything else, hit run on all of them. So there's 29 tests and they run lightning quick. So there are 29 tests here and they're running in about 0.3 seconds. So about 10 milliseconds a test. And that is lightning quick, especially if you consider how slow screenshot tests can take. So yep, fully automatable. We were happy with this. And then right to goal number 5, error-driven development. And what I mean by this is if you get an error as a developer while writing the test in the framework, that error should tell you how to proceed. So it tells you what you did wrong and how to fix it. Now to give a demonstration of that, we have a slightly more complex shader test here. So instead of just passing in the dispatch configuration, we are passing in a setup function. And within that setup function, you can set some parameters on the actual shader itself. I'll go into more detail on this later on in the talk. But suffice to say, the developer writes this, it looks right, but you'll get a compilation error. And it's not a massive big litany of template errors. It's actually just a single line, which says expected a single parameter of F shader test context reference. So it is very, very common. It's very easy to just miss out an ampersand, right? How often have we seen like performance regressions because we accidentally forgot the ampersand in a sorting functor, right? So we do as much static reflection at API boundaries of functions that are templated, as much static reflection as the language currently allows us. We're not quite at the land of static reflection proper yet, but I'm very hopeful for C++26 to get us there. So yeah, as much as we can, and then we static assert and give nice error messages. Now you'll notice here that I'm not able to actually format the message. I'm not able to say what they did wrong. I can just tell them what they need to change something to, or to make sure that the parameter is a reference rather than just passing by value. And that's because we don't really have user-generated static assert messages, right? It's currently not possible. These have to be string literals. You can't do std format or anything like that with them. At least it's not possible for us. Depending on what your development environment is, it might be possible for you right now because it got accepted into C++26. Very happy about that. We'll get there soon, maybe, possibly. And it's implemented in Clang 17 at the minute, and I think it'll be making its way to GCC 14. Still no word on MSVC yet, which is the compiler that we use. But some people might be able to use it, and I'm very excited for them. These are the links to the discussion on it, basically seeing the progression of it, and also a link to the paper. It's all of the points that Corentin brought up in his paper are basically all the things that I want. So yeah, rationale is solid there. Definitely worth a read. Now, binding extra shader resources. In the previous example, I talked about binding extra parameters, and we do a lot of static reflection whenever we're binding extra shader resources. And to give more of an example of what that actually means is if we have this test shader here called test with extra parameters, very imaginative name, and we have these parameters themselves. So we've got a byte address buffer and we've got an integer and float. So if you've got a non-static global variable in HLSL code, that is a shader binding. So that is an object that you can bind to on the C++ side to pass in information to be used within your shader. And here we're just asserting on them, essentially. So to be able to do this, you need to do a bit of extra work on the C++ side. And the nice thing about Unreal is it provides some nice macros for us to do that. So if you've written any rendering code in Unreal Engine, you'll have seen this macro here. So begin shader parameter struct, we give it a name, and then we just pass in all of the parameters that we are going to be using. So in this case, it's our byte address buffer, our uint, and our float, and we ended off with an end shader parameter struct. However, this is wrong, and we'll get a nice compilation error here out of this. It will first say the test shader that this test uses has a parameter struct which does not contain the base shader parameters. It might not shock you to believe that the test framework itself requires extra parameters to be bound, because whenever we are running asserts, what that's doing is logging some information to a buffer behind the scenes, and then we read back that on the GPU, on the CPU. So it needs its own parameters, and whenever we just use this begin shader parameter struct for ours, we're not including the ones that are required for the test. So how do we get around that? Well, thankfully, the error message continues. It says to fix this, please use begin CQTest shader parameter struct. So it's telling you that the thing you need to change, so change begin shader parameter struct to begin CQTest shader parameter struct, and that will fix things for you. And then it continues and says the line below this one is the test that uses this invalid shader. So we're telling the developer that it is the test that is signified in the next line of the error message that is the problem. So we're telling people where the issue is, what they did wrong, and how to fix it. So this is what I strive for in this framework, just to make it as easy as possible for people to write tests without having to go diving into the documentation off somewhere else. So all of this is predicated, all the static reflection is predicated on being able to detect invalid expressions. And in C++20, this is quite trivial. You just use concepts. So you have a concept here. I've just called it C has shader test parameter struct, and we have a requires clause here. And within our requires clause, we will define some constraints. And essentially, if you pass in a T to this concept and these constraints hold, so they are valid constraints with this type T, then the concept will evaluate to true and everybody is happy. So you could just static assert on this because the evaluation of a concept is a Boolean expression, and if everything is fine, turns true, everything's good. If it returns false, then the whole concept framework gives compiler writers the opportunity to provide good, helpful compilation errors. However, I did say that we don't have the luxury of C++20 just yet. So what people typically do in this situation is lean back on void T. But there's another way that I want to talk about today, which is what I would call emulating C++ concepts. So it's trying its best to make it look like it if you squint hard enough. So we start off with a non-templated struct called C shader test parameter struct. So it's the same name. And then we have a templated requires function declaration. And in this, we're just passing in a type T, just like with our concept. So if you start squinting, it's starting to look almost there. And the return type of this requires clause is a decal type. And the decal type will evaluate to this expression. So it's our constraints. So yeah, if you squint hard enough, you will see that this is somewhat concept-y like. One of the differences here is that we're using the comma operator rather than having semicolons. And the reason we're using the comma operator here is because we're sort of abusing it a bit. The result of the comma operator is the left operand and the right operand, and then it returns the right operand. But if any one of these expressions is ill-formed, then the whole expression is ill-formed. Therefore, the type that's returned by the decal type expression is ill-formed. So the whole requires function is thrown out. It is ill-formed. It does not exist. Sphene kicks in. And then to make use of this in a static assert, you don't obviously get the automatic conversion to the operator bool like you do with concepts. We instead pass this concept in to T models, which is the driver of this feature. And you can see here, this is our lovely error message whenever you get this. Now, I'm going to go through the actual implementation of this because I haven't actually seen it anywhere else, although then, again, I haven't really dived into too many template metaprogramming libraries, but I thought it was pretty neat, so I'll talk about it. So it starts off like any other templated meta function, just a templated struct called tModels, and it has a function here which will return a reference to a character array of 2 elements, so 2 characters, if the concepts requires function is well formed with the arguments passed into it. So if everything's well formed, everything passes, then this function will exist. If it doesn't resolve, if the requires clause is ill-formed, then this function will be created instead. And the difference here is that it returns a reference to an array of 1 character. So there's a size difference here, and you can probably see where I'm going with this. The output of this expression is then basically asserting that the result of resolve is of size 2. If it's of size 2, everything's well formed, everything's good. And it goes even further. You can do a little bit of, I'm not going to call it subsumption because subsumption is very complicated and it's got well-defined rules. So I'll say inheriting, so you can inherit concepts using the refines clause. And that's about it, really. And I just want to talk a little bit about a future goal I have with this framework before I end. And that is HLSL 2021. I mentioned at the start that we are stuck on 2015 for now, but I really want us to get to 2021. And the main reason for that is we get templates. And I love me some templates, but the main reason why templates is a great thing is because it allows us to program to an interface rather than to types. And if you've written any amount of automated testing in the past, you'll know that dependency injection is your best friend, right? And with templates, we get static polymorphism, which is nice way of getting dependency injection somewhat into the language. And it allows us to write much more expressive code. And it is easier to write and share HLSL libraries. But the problem is, it's a breaking change to go from 2018 to 2021. So I'm going to fight that battle, but I'm not sure how that sure how far I'll get with that one. But if you do want to see what a testing framework in HLSL 2021 looks like, look no further than mine. So I have an open source project on GitHub. Anyone can go and see it. And it's running shader tests on GitHub Actions and all of that fun stuff. So it's got a full CI and everything going, running shader code tests. And the nice thing about it is, well, the main goal of it is just to experiment and see what a testing framework can look like in this language. And I'm heavily basing everything off Catch 2. And by that I mean I'm just taking every feature that I can from Catch 2. I really like the framework, and I want to see how far you can get to it in shaders. But yeah, that's basically it. So I just want to leave you with a nice thing I like to say. Shader code is code. Please test it. And that's about it. So if there is any questions, or if there's even time for questions, I can answer them.
Hey, yeah, thanks very much. It was really interesting. We have a few questions and a few minutes for them. The first question is from Vishal Oza, who asks, can this code be used with GSL?
GLSL.
Yes, GLSL. I assume is what they mean.
I see no reason not to. It's just I haven't used GLSL since university days. I'm sorry. I've been at Rare too long.
Another question from Leslie Lai is how do assertions work on the GPU?
So assertions. So I go a lot more in depth into this in my GDC talk, but effectively at the bottom of an assertion, if an assertion fails, it'll write some data to a buffer with some sort of information on it. So the type of data that failed, the data itself, and what kind of assert that failed. And then we read that back on the CPU and then assert on that data using the underlying testing framework that we're building upon. So yeah, it's all a big lie around a readback buffer, essentially.
Cool. Question from BS Doobie: is screenshot testing still a thing? Why not just grab the state of the rendering pipeline just before all the pixels are colored?
that would be huge. Screenshot testing is still very much a thing, and it's something that we rely on quite a lot at Rare, especially on Sea of Thieves. It has been extremely beneficial throughout the development of Sea of Thieves for us. Like, it has shown up so much stuff for us and has caught a lot of things before getting to release. So maybe I can speak for us at least. It is very much a thing for us. I don't know about other studios.
Cool. And one from Das Candy. Can this be extended to GLSL, which you also already answered, but also Spear V, OpenGL, or Vulkan?
Yeah, that is something I sort of want to try, because you can compile HLSL down to Spear V and then run it in Vulkan, and that'd be something really cool. I have a pipe dream of getting that to run on my Raspberry Pi 5. Like, I think that'd be really cool to get that to run just like on on my own Raspberry Pi server. Something I want to try.
That sounds cool. And a question from Peter Nimmo for me is, speaking of Catch 2, in the future, will there be more support for testing frameworks in Visual Studio? Yes, we're still very much working on other testing frameworks for the Test Explorer in Visual Studio, and cross-platform testing, remote unit testing, all that kind of stuff. So yeah, keep your eyes out for more in that space. And then I think we've got time for one last question from Michael Volling, who asks, have you all had issues with developers forgetting to register tests? That's my biggest fear with manually registered tests.
These are not manually registered. As soon as you write that macro test class, that's it in. It's a static registration on. Yeah, so that can't happen. You can opt out. So like, you can say this test should not run on server, for example, if it's a client only thing. But it's auto registered. Yeah.
Great. All right. Well, thank you so much for joining us, Keith, and hopefully see you around.
See ya.